In the spring of 2015, I went to Princeton University to interview Professor William Happer. When I interviewed him, I was aware that he was a CO2 and its impact on climate contrarian. Mr. Happer points out carbon dioxide is an important trace gas and an integral part of the carbon cycle, a bio-geo-chemical cycle in which carbon is exchanged between the oceans, soil, rocks, and the biosphere. Virtually all of life on the planet requires CO2 concentrations to be above 150 parts per million. The concentration of CO2 in the atmosphere over the past 500 million years has been as high as 4,000 parts per million and as low as 180 parts per million. Since 1880, when CO2 was measured at Mauna Loa in Hawaii, levels have risen from 280 parts per million to 413 parts per million as of April 2019. Mr. Happer, as you will hear, says the impact of CO2 on temperature rise has already taken effect, and he points to the logarithmic scale, which is a nonlinear scale often used to analyze a large range of quantities. According to Mr. Happer, it would take another 400 parts per million to affect temperature by 1 additional degree. Mr. Happer is also aware of the folly of predictions. And he, like Freeman Dyson, points to the inability of models to accurately predict climate outcomes. Then add in the length of day, which changes by milliseconds, transferring massive amounts of energy, mostly into the oceans, causing oscillations that, according to climatologist Judith Curry, are not considered in current climate models. It begs the question, is the science of climate really settled? Can it ever be? Now, Mr. Happer's position on climate, his scientific credentials, and his role in the Trump administration have made him a very large target. He is a physicist who specialized in the study of atomic physics, optics, and spectroscopy. He is the Cirrus Fogg Brackett Professor of Physics, and he is the Davidson-Germer Prize winner in atomic or surface physics. He is not, nor could he be, a climate scientist, because that designation is so new that UCLA, for example, only just launched a degree program in 2018. Since this interview, Greenpeace outed him in a sting operation, and President Donald Trump recruited Professor Happer to be a member of a presidential committee on climate security. However, in September of 2019, the unflinching Mr. Happer quit. According to Science magazine, while Happer may have been unflinching, Trump's White House isn't. So on September the 13th, 2019, Mr. Happer resigned. Professor Happer, as you will see in this interview, firmly believes the impact of CO2 has been misrepresented.
Conversations That Matter is a partner program of the Center for Dialogue at Simon Fraser University. The production of this program is made possible thanks to the following and viewers like you. Please become a patron at conversationsthatmatter.tv.
It's not very often that we get to talk to somebody who, with your level of scientific background about climate, because when it comes to discussing climate, you actually have a sense of what's going on. And I frame that by saying sense, because I think that the topic of the science of climate is very complex. Am I right about that?
Oh yes, it's a very complicated system.
Do you understand where we're at as far as climate is concerned? Are we changing as a result of human activity? Is human activity contributing? And if so, then to what extent?
Well, of course, the climate changes all the time. It always has. And it's warmed a little bit in the last 100 years, apparently.
About 0.8 degrees
0.8
Celsius?
Maybe, yeah. Nobody knows whether that's got a human component or not. I mean, most of the warming, for example, was over by 1940, long before there was much additional CO2 in the air.
But there was a period in the late 1980s where the temperature did spike.
Indeed, there was warming of 3 or 4 tenths of a degree from 1980 to the year 2000.
But there were a couple of years in there where we had an El Nino and an El Niña effect.
Right.
Did that play a role? Do we know that for certain?
Well, you see El Niños very clearly on the temperature record. Whenever there's El Niño, the whole Earth looks a little bit warmer. That's because the Pacific gets covered with warm water that used to be all pushed together against Australia and Indonesia, but during El Niños it spreads back all the way to South America.
Right,
So,
it reverses its flow across the
that's
Pacific.
Right, yeah.
And then radiates up and down the coastline of North and South America.
There was a monster El Nino in 1998, which sort of was the peak of the warming. So that was a bit artificial. Mm-hmm. But there are El Ninos every 4 or 5 years. Yeah.
You do work with the U.S. government in helping people to understand climate. When you talk to them about the way that climate is presented, what are you telling them these days?
The government doesn't normally ask me these days, but I do tell them that climate obviously is important. It does change. There's very little evidence that humans are making much impact. And as far as CO2 is concerned, which is the major focus, that's probably more good than bad.
Now, I can hear people yelling at the screen right now saying, what do you mean CO2 doesn't make much difference?
Well, I know a lot about CO2 compared to most climate scientists because we make CO2 lasers, and CO2 is a very interesting molecule. And the particular mode of CO2 that contributes to global warming, CO2 is a rod and it bends like this, up and down, up and down. And it's that bending motion that causes the global warming. But that is such a strong absorption that it's saturated now. So as you add more CO2, most of what you can do has already been done. There's still a little addition, but not very much.
Can you explain that to me in a little greater depth? What do you mean it's already been done?
Well, if you have a barn, and you want to paint it red, if you put a thin paint of red paint, it may not be quite red enough. If you put 2 or 3, then it really looks red. After that, if you add more red, it doesn't make much difference. And so that's sort of what CO2 is doing now, that most of the easy absorption has been done. And so as you add more CO2, you get a little broadening. I don't want to get too technical.
Well, no, I find this fascinating because, and the reason that I find it fascinating is that I hear that, okay, we've gone from about 320, 330 parts per million going back in the last 100 years now to just shy of 400 parts per million if we measure it in Hawaii. And along the way, we've heard predictions of different catastrophic outcomes as we push our way through different maximums. I haven't seen them happening, even though people will attribute some weather change to that. You're saying that if we push through 400 and get to 500, the difference between 350 and 400 is greater than that between 400 and 500. Is that am I right in kind of listening?
There's an interesting thing about CO2, which is unique to CO2. It's not true, for example, of water vapor or methane, and that is that if you get 1 degree of warming from doubling CO2, so going from, say, 400 parts per million for simplicity to 800, that doubles it. Suppose that causes 1 degree of warming. Then to get another degree of warming, you have to double 800, so you have to go to 1600. So you have to double it again. So it gets harder and harder to warm. Technically, they call that the logarithmic dependence of temperature rise on CO2 concentration. It was first guessed at, really, by Svante Arrhenius, who did some of the earliest work on global warming. He thought it was good, he was all for global warming. But he was the first one to point out this doubling property of CO2. Nobody quite knows how he guessed it. It's correct.
Because he wasn't using computer models.
Well, it was before quantum mechanics. He didn't even know about spontaneous emission. It was before Planck. But nevertheless, he guessed it correctly.
It's quite remarkable, isn't it?
Quite a guy, yeah.
Conversations That Matter is brought to you by Odlum Brown, a client-focused investment firm that starts client relationships with straightforward conversations focused on you, your aspirations, and your investment priorities. Audlin Brown has been a supporter of Conversations That Matter from the day we started this show. Their only condition was that we provide a non-biased conversation with people from all sides of all sorts of issues. And of course, we couldn't produce this show without the support of Oh Boy Productions. If you're looking to produce a show like this one, I suggest you reach out to Oh Boy. They can help you produce it, and they can help you build your audience. And we also need your support. I ask you to please pledge $1 per show by going to conversationsthatmatter.tv/donate, because those dollars add up and play an important role in helping us produce this show. Now, back to the show. So, CO2, you know quite a bit about it.
Yeah.
Is it all negative? And if not, then what are the benefits?
Well, I think the main benefit of CO2 is it's the food for plants. Plants really need three things. They need light for photosynthesis, they need water, and they need CO2. Plants are made of carbon. You know, when I hear about carbon pollution, you know, we're all made of carbon. Plants are made of carbon, people are made of carbon, you know, your hamburger's made of carbon. But CO2 is used by plants. If you go to a cornfield, for example, in midsummer, and you measure CO2, it's about half what it would be at night, because the corn plant has sucked so much CO2 out of the air that it's now limited on how fast it can make new sugar and grow by the amount of CO2. So if you double the CO2, the corn can grow better. There's more of it there. It doesn't suck it down so quickly. So that's number one, is it's an essential plant food. And the other thing is it gives drought resistance to plants. Because a plant has this problem that when it gets CO2, it doesn't suck it up from the roots. It has to open up little holes in its leaf, and so CO2 molecule bounces around and other air molecules gets into the hole. For every CO2 that goes into this hole, 100 water molecules may diffuse out from the interior of the plant. So the plant is squandering water as it's trying to, you know, make food, you know, from photosynthesis. So if you look at, say, a gram of sugar, to make a gram of sugar takes 100 grams of water. You know, so there's huge amounts of water used in photosynthesis now, more than should be, because we're essentially in a CO2 famine. If you look at
we're in a CO2 famine.
Famine. We have too little CO2.
So at 400 parts per million.
400 is still too small. Yeah. If you look at the geological history of the world, you know, we started getting good fossils about 550 million years ago, Cambrian. Yeah. Since that time, CO2 levels have averaged thousands of parts per million, not a few hundred parts per million, you know, much, much higher, factors of 4, 5, 10 even. And so plants really evolved when there was a lot more CO2 to eat. You know, now they don't have enough. And you can see lots of evidence for that. There's certain plants, for example, that they're called C4 plants that are adapted to the low CO2 levels we have now. They typically are in hot regions of the earth. Sugarcane is an example. Corn, American corn, maize is another example. But most of our agricultural plants use the old-fashioned photosynthesis, which is called C3. And that's a more efficient way to operate if you have plenty of CO2, but there isn't plenty of CO2 anymore. There's not enough. So as CO2 levels have been going up, the old-fashioned C3 plants, and that includes soybeans and weeds and cotton, actually most plants are C3. They're doing very, very well. I mean,
with an increase in CO2.
With the increase in CO2, very, very noticeable. It's a huge effect. You know, it's worth hundreds of billions of dollars every year in agricultural productivity. So when people talk about the social cost of carbon, it's absurd. You know, the social cost is negative of CO2. Now
because it's a net contributor.
It's a net contributor to agricultural productivity. That's not. You shouldn't confuse that with real pollution from a coal plant. You know, a coal plant, if you don't build it right, it scatters fly ash all over everybody. It may have sulfur, and, you know, all sorts of horrible things can come out. But the CO2 is actually good.
But we're not paying attention these days to that coal plant so much.
Yeah.
So much of our focus seems to be on man-made global warming.
Yeah, yeah.
And do you think that we're missing the appropriate target right now?
Yeah, I mean, it's another one of these sort of mass hysterias that have gripped humanity since it began. You know, in our country, in America, we had a sort of similar case of mass hysteria with prohibition. There were a few cautious people who said maybe, you know, prohibition isn't a good idea, you know, it might increase organized crime, for example. Yeah, everything they said was right, and yet, you know, when the amendment for prohibition was put to the vote, every state except one, Rhode Island, voted for prohibition, and not one of them intended to honor it, you know. It was just what everybody else did. You know, how could you be in favor of demon rum, you know, demon CO2? So these things happen, you know. More sinister are these movements in Europe, you know, the fascists, you know, the communists, they were mass hysteria too.
Mm-hmm. Mm-hmm. Well, and with true catastrophic consequences.
Indeed, yes, yes. Any movement can be captured by thugs, and that's what's happened.
So you've talked about the benefits of CO2.
Mm-hmm.
Is there a downside? Because there has to be. When we listen to the level of discourse about this, how can there not be some downside?
I don't think there are any real downsides. I mean, if you look at the arguments, the initial argument was there's going to be this rapid global warming. It hasn't happened. So it's very clear that the models have enormously exaggerated the warming potential.
Why has that happened? What is it about the models that when you simulate it works and you say, well, there it is?
Well, I mentioned the saturation of CO2. You know, if you paint the barn red, if you put another coat, it's not any redder than it was before. And they noticed that early on, that CO2 has this problem that, you know, it's disappointing that it doesn't seem to make much difference if you had. So they invented all sorts of feedback mechanisms that would amplify the effect of additional CO2. Water vapor, clouds, all sorts of things were supposed to be triggered by the CO2. They don't seem to be happening.
But water vapor is a dominant greenhouse gas anyway.
Water vapor is the main greenhouse gas. Water vapor and clouds.
It is the greenhouse gas, isn't it?
Yeah, 70% maybe. Yeah.
I have talked to somebody else who is a climate scientist and said, no, clouds aren't in the equation. But how can they not be in the equation?
Well, it depends on the model. I mean, the most professional modelers, those trying to do the most honest job, do try to put in clouds, but it's very primitive, you know, it's a rough estimate. There's nothing. My
own journey with trying to understand climate science started when I watched Al Gore's movie, An Inconvenient Truth.
Yeah.
Mr. Gore says that if you take water vapor out of the equation, and he says it rather casually, if you take water vapor out of the equation, CO2 makes up 30% of greenhouse gases. And I went, holy smokes. So I started to do some investigation and went, okay, well, he's right about that, but you can't take water vapor out of the equation. And you can't, and if you do, are you then not negating the dynamic interaction between CO2, methane, water vapor, and the other greenhouse gases that are involved? Yeah.
No, of course you can't take water vapor out, and you should always be careful to say water vapor and clouds. Clouds are big deal.
How come? What makes them a big deal?
Well, if you just go to space and look at the Earth, you don't see the ground over big fractions of the Earth. All you see is clouds.
But if you take a look, if you take a look at the Earth, that beautiful blue bubble or marble in space,
it's marble because the white part of the marble is clouds.
but that image that's on Al Gore's book doesn't show so much cloud cover as a result of global warming.
Well, that bothered Al, so he airbrushed a lot of the clouds out. You know, if you look at the original papers, they have many more clouds. I mean, I can show you if you like.
You say it's been airbrushed out?
Yes.
And what about the ice on the caps of the Earth, both the Antarctic and Arctic?
Antarctic ice is probably growing. You know, it's a big, complicated continent. West Antarctica, maybe there's a little decrease, but over most of Antarctica, it's increasing.
Well, I was just
sea
reading...
ice is increasing around Antarctica.
Yeah.
That's not supposed to happen, you know, according to the models, but it is happening.
And what's happening in the Arctic?
Well, there's a good website, I think it's called Cryosphere or something at the University of Illinois. And if you Google on it, you'll find it.
Cryosphere.
Cryosphere, and they're pretty honest, I think. And so you can look at the ice this year or last year, and you know, it fluctuates up and down. There's a lot of ice now because we're just coming out of the Arctic winter.
And a particularly cold one, too.
Yes, yes, yes. But the other thing to remember about the Antarctic, it's all water. It's completely different from the South Pole. You know, you've got this Arctic Ocean up there, which lets heat come in by warm water from the Atlantic in particular. And so much of what's happening in the Arctic is really determined by ocean currents, not by the air temperature or things like that.
So over the course of the Earth's history, ocean cycles and flow have played a significant role in temperature.
Still do. Yeah.
So here's one of the things that I hear when people try to explain the pause in increase in temperatures. Well, it's because the Earth's oceans are absorbing that extra heat, and of course it is now circulating through the flow of the oceans, and this is why we're seeing melt not only in the Arctic, but in particular in Greenland. And yet, I read a report just last week released by NASA that said, nope, the deep ocean temperatures haven't changed at all.
It's hard for the deep ocean temperature to change much because, you know, the heat has to be convected down there. It won't conduct, you know, much too slow. So the only way to change the deep ocean is from water that is sinking up off Greenland or off the South Pole.
Yeah.
And those are very slow measured currents that slowly move. And so it's extremely difficult to heat all of the ocean. It's quite easy to heat the first few inches, you know, or first few meters, you know, down to the thermocline, but it's much harder to get below that. So that has to be done by currents, which the other answer you should give when people say that is, well, if that's the case, why is it all these 70 models or whatever it is, you know, expensive computer models didn't predict that, you know? You know, they all promised they would predict what would happen to the temperature. You know, none of them got it right. Not only did they not get it right, they got it wrong by a huge amount, you know, factors 3, 4.
Do you have any sense of why how they could be, so many models could be so far off?
Well, yes, I mean, it was groupthink. The models never looked at the world, they looked at other models. And so they used to say, look how good we are, man, we're all getting the same answer, it must be right, you know, we're agreeing with each other. But then if you look at the models, they've all got different parameters, they've all been coded in different ways, and the reason they're giving the same answers, they look at each other and say, oh, I'll adjust this parameter and this one, and now it gives the same answer. And
so as we look to the future, are you hopeful that the world is going to continue to be a safe place, that we will do the things that are necessary to protect this precious planet, but that climate is not going to be the overwhelming catastrophic event that some people proclaim that it might be?
Yeah, I don't think there's anything to worry about from more CO2. I'll say it again, that I think more CO2 will be good for the world, that our great-grandchildren will look back and say, thank God we've got all this CO2, you know, what foresighted people our ancestors were. I think it is true that you can mess up the world very easily. You know, the American rivers used to be a disgrace. When I first went to New York City, you know, Hudson River was an open sewer, and it's clean now. There are salmon running up the river, shad every spring, you know, and so that's the type of environmentalism that works and is good for us, and that's what we ought to be working on, cleaning up real things that make a difference.
Well, thank you very much for your
Yeah.
time. I really appreciate this. Thank you.
Pleasure, yeah.